Okay, welcome to this video on absolute value and piecewise defined functions. This is part of a Unit 2 in our honors algebra class for systems. And absolute value can be written as a system of two piecewise defined functions. So it kind of is a good kind of bridge and a good place to put in this little side topic that really doesn't go anywhere else very well. So we are going to do it here. So before we do this, the first thing we're going to do is, I know you've graphed absolute value before, but we're going to define the parent function and then work with that a little bit. Okay, so the parent function of absolute values is f of x equals absolute value of x. So that is absolute value, meaning distance from 0. And we're going to plug in some points. I'll do a couple negatives and 0 and a couple of positives. Okay, just randomly chose some numbers. So the absolute value means distance from 0. So the absolute value of -4 is 4, of -1 is 1, 0 is 0, 1 is 1, and 4 is 4. So let's plot this. -4, 4, -1, 1, 0, 0, 1, 1, and 4, 4. And we can see that when we graph this, it makes a rather sharp V shape. I always joke the absolute value, V stands for the shape it makes, a shape of a V. The domain of this is x is equal to all real numbers, or in notation, that would be -infinity to infinity. Okay, interval notation, that was what I was looking for. Now the range starts at 0 and goes to infinity, or you could say y is greater than or equal to 0. And the vertex is at 0, 0. It has a vertex like a parabola, so it shifts exactly the way a parabola does. So, as I have said here, absolute values can be transformed like a parabola with your regular function transformer here. So we are going to use transformations on the parent function to graph this one. So I'm just going to plot very lightly the original one that we graphed so we can see what happens when we graph our new one. Make it very, very light as possible as I can here. Okay, so because it's transforming by -4 plus 3 and -1, first, remember we do CBAD, right? So this is C, so that means it moves right 4. There's no B because B is 1. A is -1, meaning that it reflects vertically over the x-axis. And then the plus 3 means that it shifts up 3. So if I take this center vertex form and I move it right 4, I flip it over the x-axis, well, it's on the line of reflection, so it stays, and then it goes up 3. It's going to end up here. And that will happen with any other point. And that means that it's going to be going, making a sharp V shape down like this. All right, and there's our transformed parabola. I mean, not parabola, absolute value function. Okay, so now let's talk about what a piecewise defined function is, generally speaking. This did not show up when I tried to type it, so we're just drawing that in. So a piecewise defined function is when basically you're graphing a different function. We have 3 here, but only on a certain domain. Okay, so I'm graphing the function. The first function that I am graphing is y equals 9, which is a horizontal line. X is less than or equal to -3. So if I go to y equals 9, if I was to plot the whole line, okay, so here it is, 9. Okay, but I don't need the whole line. I just need the part that starts at -3 and goes to the left. So the only part of this line that I actually need is all the way up to -3. And it says or equal to -3. So that point gets a closed circle. It's part of the graph. So that's the first section of my graph. Then the next section is x squared. It's a parabola. I'll just put a dot here to note the color I'm doing it in. All right, so now I will go graph the parabola portion. Y equals x squared. Well, y equals x squared is your basic parent parabola. And we're going from -3 to +2. -2, 4, -3, 3, and then +2, 4. Okay, but this point is not included, so it's an open circle. And here it's not included, but it's already included with the green one. See, where something starts and stops at the same number, we want to make sure on one of them it has the equal part and on one of them it doesn't. Especially, I mean, only if they coincide at the same point. I'll show you what I mean about that in a minute. Because if you have 2 points at the same place, of course, it would not be a function. So the point -3,9 is part of the function overall, but only in that it is part of the part that's the horizontal line. So 3 is not included with this one, but that's because it is included with the green one. All right, now let's do this part. 1/2 x plus 3. 3. Up 1 over 2, up 1 over 2, up 1 over 2, up 1 over 2, and so forth and so on. And they only want us to graph it for values greater than or equal to 4. So actually, it's just this portion of the line. So we've put together that graph of this piecewise defined function. All right, so you should be able to graph one, or if I gave you a graph, you should be able to make up the equation. All right. Now let's talk about how absolute value functions and piecewise functions can come together. Absolute value functions can be written as piecewise defined functions made up of 2 linear functions, because we know that shape of a V has 2 lines, the left part and the right part. Here's how you write it. F of x becomes, absolute value of x becomes what's inside if n is greater than or equal to 0, and the opposite of what's inside if the inside is less than 0. We actually are going to use that process to write the 2 equations. So let's do it with this first one, and then we'll graph it on Desmos just to confirm that it worked. I want you to be able to see the notes while I do this. Here we go. There we go. So f of x equals absolute value of n, and it can have a, b, c. I mean, it can have the other stuff, equals a absolute value bx plus c plus d. You could redefine this and say it's a parentheses bx plus c plus d if bx plus c is greater than or equal to 0. And it's negative a, because you'd have to multiply a negative through, times bx plus c plus d if bx plus c is less than 0. And again, I only have the equal on the top part so that they don't overlap with the same point and become not a function. But the equal part could be with the bottom one. It just not can't be with both, and it can't be with neither. You can't leave the vertex out. All right, so let's work out this first one here. All right, so we know that f of x is going to equal x minus 4 minus 3 if the part inside x minus 4 is greater than or equal to 0, which means it's going to equal x minus 7 if, because I just combined those, x is greater than or equal to 4 if I divide or add 4 to both sides. So that's one of the 2 that's going to go in my piecewise defined function. It's going to equal the opposite of x minus 4 minus 3 if x minus 4 is less than 0. I'm doing the second part of this now. So negative x plus 4 minus 3 means negative x plus 1 if x is less than 4. That's the second part of my piecewise defined function. So to write my entire piecewise defined function, which I should technically be calling this f of x to be a function, it's x minus 7 if x is greater than or equal to 4. It's negative x plus 1 if x is less than 4. That's my piecewise defined function. So let's check this on the Desmos. All right, if I go to my graph that I set up, I'm going to turn these off. We don't need them yet. We'll need them later. Here was the original absolute value equation. My first line was here that I got, and you can see that it totally coincides with the purple graph. If you change it, just changes color. And here's the other side of it that we got. And so it totally matches. So it's definitely correct for our equation. Okay, so there's another one you're going to try right now. I would invite you to pause the video, do this problem, and then come back and check it. All right, so let's play that same game with this. Here we go. All right, so for this, it's going to equal exactly the same. Oh, it's not absolute value. I'm going to change it to parentheses now because it's like I'm saying positive of it if it's positive greater than or equal to 0, and negative of it if it's less than 0 negative. If the inside is greater than or equal to 0. So we need to make sure we simplify that. Negative 2 times 2x is negative 4x plus 8 plus 1. If 2x is greater than or equal to 4, I'm solving it a little bit at a time. It's going to equal negative 4x plus 9 if x is greater than or equal to 2. So that's the first part of my piecewise defined function. Then it's going to equal the opposite of this, which is negative 2 times negative 1 times 2x minus 4 plus 1 if 2x minus 4 is less than 0. Okay. So that's 2 times 2x minus 4 plus 1, which is 4x minus 8 plus 1, which is 4x minus 7. If 2x is less than 4, x is less than 2. Okay. Less than 2, not less than or equal to, sorry. That's the second part. So our function would be f of x equals negative 4x plus 9 if x is greater than or equal to 2, or 4x minus 7 if x is less than 2. So let's go look at that on the Desmos. I pre-typed everything in. So there's the original function, and here's the two that we got when we went through the process, and they do totally match that function. Okay. So let's look at two functions that also have to do with, oh, wait a minute. I don't think we're done with this yet. Sorry. Yeah, we're not ready for that yet. We have to go back up and finish this. All right, so now that we've done a couple of problems with the absolute value equations, let's look at an application function. So we have the Sydney Harbour Bridge in Australia is 1,149 meters long, all right? Because of changes in temperature, the bridge can expand or contract, when it gets really, really hot or really, really cold outside. The length of the bridge at any moment can be represented by x. Write an absolute value function, y equals f of x, that would give the amount the bridge varies from its length at any measured moment as a function of length of the bridge at that moment. So in other words, the amount the bridge varies is basically going to be the difference between this amount and what it measures at a particular moment, which is x, okay? So the variation y is going to be the difference between what you measure and 1149. And you can subtract it in any order. You can do x minus 1149 or 1149 minus x, because when you take the absolute value, it's going to take that measured distance and make it positive. So it doesn't matter if the bridge is contracted a little and x is smaller, or it's expanded a little and x is bigger. I did graph that function on Desmos. It's just a basic absolute value function that has been shifted to the right. Oh, I lost it. To the right, 1149. So let me just show you that real quick. and then we're going to do some stuff with it. That is on this one. So here's that basic function that's been shifted to the right. I don't even have my y-axis because it's way to the left. You can't see it. All right, so we did that. We'll just say check. We did that. Okay. Use a vertical or horizontal line on Desmos to find out what the variation is when the bridge measures 1151. So they're giving us an x value of 1151. So that means in this case, I'm going to use a vertical line to find out what that's going to be. So I'm going to turn that line on. I was already ready for it. Let's see. Where does it intersect? Right here at 2. Okay, so that means the variation is 2. And what is the units we are measuring in? I am uncertain about this. Meters. Okay, so it says meters in the problem. Which makes sense because 2 meters is the difference between 1151 right here and 1149. It's 2 meters apart. All right, now we're going to use a vertical or horizontal line to find out the possible measures of the bridge. So that means the measures of what x is when the variation, I'm giving you y, is 0.42. So we're going to graph the line y equals 0.42. So in other words, it could be 0.42 bigger or 0.242 meters smaller than what the measure of the bridge is at like a centralized temperature that's been decided on. So we're going to go graph that line on Desmos and take a look at that. I'm going to turn this one off and turn this one on. And so we can see that we have 2 places that happens because we're doing a horizontal line because we're getting y equals 1148.58 or 1149.42. So you can go over 0.42 or under 0.42. So we're going to write those down. So we did a horizontal line. Sorry. Okay, and we got 1148.58 or 1149.42. Okay, so there is an application involving absolute values. Okay, the other 2 functions we're going to talk about right now, and then we're done with this lesson, are the greatest integer function and the least integer function.